Hello there, and welcome to the Drowsy Inquirer. I'm so glad you found your way here tonight, because we are about to witness something extraordinary. Tonight we are going to watch the sky catch fire, not with flames, not with heat, but with light so strange, so silent, so impossibly beautiful that people who see it for the first time often forget to breathe. Tonight we are exploring the Northern Lights. Imagine standing on a frozen plain somewhere above the Arctic Circle. The air is so cold it stings your nostrils with every breath. The snow beneath your boots creaks with each step. Above you, the sky is black and impossibly clear, filled with more stars than you have ever seen. And then, slowly, so slowly, you are not sure it is happening at all. A faint green glow appears near the horizon. It grows. It stretches. It lifts itself upward like a curtain being drawn across the sky by an invisible hand. The green deepens, brightens, and begins to move. It folds and ripples, like silk caught in a breeze that you cannot feel. A second curtain appears behind the first, this one edged in violet. Then a third, higher still, tinged with red. The entire sky's alive now, shifting, breathing, dancing in complete and perfect silence. This is the Aurora Borealis, and tonight we are going to understand it. We will begin with what your eyes would see if you stood beneath the lights, and then we will trace the story backward through the atmosphere, through the invisible magnetic shield that surrounds our planet, across 150 million kilometers of empty space, all the way to the surface of the sun, where the whole story begins. We will learn why the lights are green and sometimes red and sometimes violet. We will hear the myths that ancient cultures created to explain them. And we will discover that auroras are not unique to Earth, that they dance on Jupiter and Saturn, and even on moons that orbit other worlds. Some of what you hear tonight may surprise you. Some may fill you with a quiet sense of wonder. And some may simply drift past you, soft and unhurried, like light moving slowly across a winter sky. If this kind of gentle exploration helps you relax or find your way to sleep, consider leaving a like or subscribing. It helps other curious minds find their way here too, one quiet night at a time. But for now, let your body settle. Let the day fall away, and let us step together into the longest, darkest, most beautiful night you have ever imagined. When the sky moves, and no one told you it could do that, there is a moment that almost everyone who sees the Northern Lights for the first time describes in the same way. It is not the color that strikes them first, though the color is extraordinary. It is not the scale, though the lights can stretch from horizon to horizon. It is the movement. The sky moves. It ripples and folds and breathes. It does something that the sky, in your entire life of looking up at it, has never done before. Stars are still, clouds drift slowly, the moon arcs across the heavens at a pace too slow to notice. But the aurora dances. It shifts and changes in real time, right before your eyes, fast enough to follow but too fluid to predict. Curtains of light sway like fabric in a wind that exists 100 kilometers above your head. Waves of green pulse across the sky like breath, like a heartbeat, like something alive. People cry, not from sadness, but from the sudden, overwhelming realization that the sky can do this, that it has always been able to do this, that this was happening somewhere, on every night of their lives, and they simply never knew. No photograph can capture it. Photographs freeze the light in place, strip away the movement, the scale, the biting cold, the silence. They give you the color, but not the experience. The experience is standing in the dark, your neck craned back, your mouth slightly open, watching something that seems too beautiful to be real, and knowing with absolute certainty that it is. Every aurora is different. Some nights the lights are faint, a pale green smudge near the horizon that could be mistaken for distant city glow. Other nights they explode across the entire sky, green and violet and red, folding and unfolding so rapidly that you cannot look in every direction at once. The aurora does not perform on schedule. It does not guarantee a show. You travel to the Arctic, you wait in the cold, and you hope. And when it comes, if it comes, it is worth every frozen minute. They are silent, and that silence is part of the magic. One of the most remarkable things about the aurora is what it does not do. It does not make a sound. The most dramatic light show on the planet, curtains of luminescence stretching hundreds of kilometers across the sky, shifting and pulsing and folding with visible energy. And it happens in absolute silence. This feels wrong. Your brain expects a spectacle of this magnitude to be accompanied by something, a roar, a hum, a crackle. And the northern lights look like they should sound like a campfire, or like distant thunder, or like the hiss of electricity. But there is nothing, just the light, and the dark, and the cold, and the quiet. The silence changes the experience profoundly. Without sound, the aurora feels dreamlike, almost hallucinatory. It creates a strange intimacy between the viewer and the sky, as if the lights are performing for you alone, whispering something in a language you almost understand. There are, however, persistent reports from some observers of faint sounds during very strong auroral displays. Crackles, hisses, quiet popping noises. For centuries, scientists dismissed these reports as imagination or as sounds from the environment being attributed to the lights. But in 2012, Finnish researchers placed microphones at an observation site and recorded faint crackling sounds that correlated with auroral activity. The sounds appeared to originate at about 70 meters above the ground, far below the aurora itself. The leading hypothesis is that these sounds are caused by electrical discharges near the ground surface, triggered by the rapid changes in the geomagnetic field during intense auroral activity. The aurora itself, 100 kilometers overhead, remains silent, but the electromagnetic disturbance it causes may, in rare cases, create faint sounds much closer to the listener. Whether you hear them or not, the dominant experience of the aurora is silence, a sky on fire, and not a whisper. It is one of the things that makes the northern lights feel less like a natural phenomenon and more like a secret. The colors are not what most people expect. If your impression of the aurora comes from photographs, you probably picture vivid, saturated bands of bright green and electric purple painted across the sky. The reality is more subtle, more varied, and in many ways more beautiful. The human eye and a camera sensor respond to light very differently. Camera sensors can accumulate light over several seconds of exposure, brightening faint details and saturating colors that the eye perceives as muted. The result is that photographs of the aurora are often more vivid than what you would actually see standing beneath the lights. A weak aurora may appear to the naked eye as a pale grayish-white glow near the horizon, almost like thin cloud illuminated from behind. You might not even recognize it as an aurora at first. The green tint is there, but it is subtle, washed out, more suggestion than statement. A moderate aurora brings the green to life. You can see it clearly now, unmistakably green, moving and shifting against the dark sky. But it may not be the electric neon green of photographs. It is softer, more natural, like light filtered through leaves. A strong aurora, driven by a powerful geomagnetic storm, is where the photographs begin to match reality. The green becomes vivid and bright. Violet and purple edges appear. In exceptional storms, deep reds bloom at the top of the display, and pinks and oranges flicker along the lower borders. These strong displays are genuinely breathtaking, and they are the ones that make people cry. The difference between the eye and the camera is not a disappointment. It is a reminder that the aurora is a real physical phenomenon, not a digital creation. It lives in the sky, shaped by real atoms and real physics, and it is beautiful in the way that real things are beautiful. Not perfect, not uniform, but alive. Green is the most common color, and oxygen is the reason. The signature color of the Aurora Borealis, the color that defines it in the popular imagination, is green. A particular shade of green, bright and clear, and unlike any green you see in everyday life. It is the green of excited oxygen. When a high-energy electron from space collides with an oxygen atom in the upper atmosphere, at altitudes between roughly 100 and 300 kilometers, the collision transfers energy to the oxygen atom. Specifically, it kicks one of the atom's own electrons to a higher energy level, an unstable, excited state. The atom wants to return to its ground state, its comfortable, low-energy configuration. And when it does, it releases the excess energy as a photon, a particle of light. The photon released by this particular transition in oxygen has a wavelength of 557.7 nanometers. This is the green line of atomic oxygen, one of the most well-known emission lines in all of spectroscopy. It is this specific wavelength, this specific shade of green, that paints the sky during most auroral displays. Every green photon you see in an aurora was born from the same process. A single electron, accelerated by the sun and guided by the Earth's magnetic field, struck a single oxygen atom in the thin upper atmosphere. The atom absorbed the energy, held it for a fraction of a second, and released it as a tiny flash of green light. One atom, one photon, one flash. Multiply this by billions, trillions, and countless atoms all excited at once, and the individual flashes merge into the sweeping green glow that fills the sky. The green of the aurora is not reflected sunlight. It is not scattered light. It is not an illusion. It is light created right there, in the atmosphere, by individual atoms doing something as simple and as beautiful as returning to rest. Red auroras come from oxygen too, but much higher up. The same oxygen atom that produces the familiar green aurora can also produce a very different color, a deep, rich red. The difference is altitude. Above 300 kilometers, the atmosphere is extremely thin. The oxygen atoms are so far apart that an excited atom can hold on to its excess energy for much longer before releasing it. In this rarefied environment, the oxygen atom undergoes a different electronic transition, and one that produces a photon with a wavelength of 630 nanometers deep red. This transition is what physicists call a forbidden transition. It is not truly forbidden, of course, since it clearly happens, but it is extremely unlikely under normal conditions. The atom must remain in its excited state for up to 2 minutes before it emits the red photon. At lower altitudes where the atmosphere is denser, the atom would collide with another molecule before those 2 minutes were up, losing its energy to heat rather than light. The red photon would never be born. But at 300 kilometers and above, there is so little surrounding gas that the atom can wait. It holds its energy patiently, undisturbed, and eventually releases it as a soft red glow. Red auroras are rare because they require very energetic particles to penetrate to those extreme altitudes, and such particles are only abundant during the most powerful geomagnetic storms. Throughout history, red auroras appearing at lower latitudes, where people had never seen any aurora before, were interpreted as terrifying omens. In medieval Europe, a red sky in the north was seen as a sign of blood, war, or divine anger. In China and Japan, red auroras were recorded as portents of disaster, famine, or the fall of dynasties. The color red, appearing without explanation in the night sky, spoke to something primal in the human imagination. Today we understand that a red aurora is simply oxygen doing what oxygen does, releasing energy as light at a wavelength determined by the laws of quantum mechanics. But the sight of it, A deep crimson glow spreading across the northern sky remains as arresting now as it was 1,000 years ago. Purple and blue come from nitrogen. Oxygen is not the only gas in the atmosphere, and it is not the only one that produces auroral light. Nitrogen, which makes up 78% of the atmosphere, contributes its own colors to the display, primarily in shades of blue, violet, and occasionally pink. When a nitrogen molecule, N2, is struck by a high-energy particle, it can become ionized, losing one of its electrons entirely. The ionized nitrogen molecule emits light in the blue and violet part of the spectrum, producing the purple and magenta tones that often appear along the lower edges of auroral curtains at altitudes around 100 kilometers. Neutral nitrogen atoms, as opposed to molecules, can also be excited by particle impacts. When they return to their ground state, they emit light in the red and pink part of the spectrum, different from the red of high-altitude oxygen. This nitrogen red is often seen as a pinkish fringe at the very bottom of the auroral display, where the incoming particles have penetrated deepest into the atmosphere. The result is a layered palette. At the top of the aurora, above 300 kilometers, you may see the rare red glow of high-altitude oxygen. Below that, the dominant green of oxygen at intermediate altitudes, and at the bottom the blue and purple of ionized nitrogen, sometimes edged with the pink of excited neutral nitrogen. Each color tells a story. It tells you which gas is glowing, at what altitude, and with what energy. The aurora is not a single phenomenon, but a vertical cross-section of the atmosphere, illuminated from within, each layer contributing its own voice to a silent symphony of light. If you know the colors, you can read the atmosphere like a book, written in photons, authored by the sun. The shapes have names and each one reveals the magnetic field. Auroras do not appear as a uniform wash of color across the sky. They take specific, recognizable forms, and each form reflects the geometry of the magnetic field lines along which the charged particles travel. The simplest and most common form is the auroral arc, a long, thin band of light stretching roughly east to west across the sky. An arc is typically quiet and stable, glowing steadily without much movement. It marks the boundary of the auroral oval, the ring-shaped zone of auroral activity that encircles each magnetic pole. When the arc begins to develop waves and kinks, it becomes a band. Bands are more dynamic than arcs, folding and rippling as the magnetic field fluctuates. They can develop ray structures, vertical streaks of light that extend upward from the band like the teeth of a comb, each ray aligned along a magnetic field line. The most dramatic form is the auroral curtain, a broad, tall sheet of light that appears to hang from the sky like fabric. Curtains fold and sway, creating the appearance of drapery caught in a cosmic wind. When you see time-lapse videos of the aurora moving rapidly across the sky, it is usually curtains that you are watching. And then there is the corona, a formation that occurs when the aurora is directly overhead. Looking straight up into a curtain or a series of rays, perspective causes the lines to converge toward a single point, like railroad tracks meeting at the horizon. The result is a radial burst of light appearing to stream outward from a point directly above you, filling the entire sky with radiating beams. It is, by many accounts, the most awe-inspiring auroral form, the moment when the sky seems to open and pour light directly down onto you. Each of these forms is not just beautiful, but informational. The shape of the aurora tells scientists about the structure of the magnetic field, the energy of the incoming particles, and the state of the magnetosphere. Every fold, every ray, every ripple is data written in light. The aurora begins 150 million kilometers away. Everything you see in the northern sky on an auroral night, every green curtain, every violet edge, every red glow, began its journey not in the atmosphere, not in the magnetic field, but on the surface of a star. Our sun is not a gentle, steady lamp. It is a thermonuclear furnace 400 times wider than the Earth, with a surface temperature of 5,500 degrees Celsius and a core temperature of 15 million degrees. It converts 600 million tons of hydrogen into helium every second, releasing energy equivalent to billions of nuclear weapons detonating simultaneously. It has been doing this for 4.5 billion years and will continue for another 5 billion. But the sun is not just hot, it is turbulent. Its surface is a roiling ocean of plasma, in an electrically charged gas so hot that atoms are stripped of their electrons. This plasma is threaded with magnetic fields of extraordinary complexity, fields that twist, tangle, snap, and reconnect in a continuous, violent dance. It is this magnetic activity that drives the aurora. The sun does not simply shine, it breathes. It exhales a constant stream of charged particles into space, and occasionally it screams, hurling billions of tons of magnetized plasma outward in explosions that can cross the entire solar system. Some of that plasma, some of that magnetic breath, reaches Earth, and when it does, the sky responds with light. The aurora is a message from the sun. It is written in particles, delivered across 150 million kilometers of vacuum, translated by the Earth's magnetic field, in and read by the atoms of our atmosphere. Every auroral display is a conversation between a star and a planet, conducted in the language of physics, visible to anyone willing to stand in the cold and look up. The sun is not a calm, steady star. From Earth, the sun appears constant. It rises, it crosses the sky, it sets. Its light seems uniform, unchanging, reliable. But this impression of serenity is an illusion of distance. Up close, the sun is one of the most violent objects in the solar system. The visible surface of the sun, called the photosphere, is covered with granules, convection cells roughly 1,000 kilometers across. Each granule is a column of hot plasma rising from below, spreading outward, cooling and sinking back down. The photosphere is in constant motion, bubbling and churning like the surface of a pot of boiling water, except that each bubble is the size of a country. Above the photosphere lies the chromosphere, a thin layer visible during solar eclipses as a reddish ring. And above that lies the corona, the sun's outer atmosphere, a vast halo of plasma extending millions of kilometers into space. The corona is, paradoxically, far hotter than the surface below it, reaching temperatures of 1 to 3 million degrees Celsius. The exact mechanism that heats the corona to such extreme temperatures remains one of the open questions in solar physics. The corona is not smooth or uniform. It is structured by the sun's magnetic field into loops, arches, and streamers. Where magnetic field lines are closed, looping back to the surface, the plasma is trapped and glows brightly. Now, where the field lines are open, extending outward into space, the plasma escapes, streaming outward as the solar wind. The sun is a magnetic engine. Its energy output in light is remarkably steady, varying by only about 0.1% over its 11-year cycle. But its magnetic output is wildly variable, and it is this magnetic variability that drives space weather, solar storms, and ultimately the aurora. Solar wind blows constantly from the sun. The sun is continuously losing mass. Every second it sheds roughly 1.5 million tons of material into space, not as light, but as a stream of charged particles, primarily electrons and protons, flowing outward in all directions. This is the solar wind. The solar wind travels at speeds ranging from 300 to 800 kilometers per second. At its fastest, and it could cross the distance from the Earth to the Moon in about 8 minutes. It takes the solar wind roughly 2 to 4 days to travel from the sun to the Earth, depending on its speed. The existence of the solar wind was predicted in 1958 by the physicist Eugene Parker, who argued that the sun's corona was so hot that it could not be gravitationally contained. The corona must be expanding outward, he reasoned, creating a continuous flow of particles into space. His prediction was controversial at the time. Many physicists were skeptical, but in 1962, the Mariner 2 spacecraft, on its way to Venus, directly measured the solar wind and confirmed Parker's prediction in every detail. The solar wind is not uniform. It has fast components and slow components, dense streams and thin ones. It carries with it the sun's magnetic field, and stretched and twisted into a vast spiral pattern by the sun's rotation, called the Parker spiral. This interplanetary magnetic field extends throughout the solar system, connecting the sun to every planet, every asteroid, every grain of dust. When the solar wind reaches Earth, it encounters the magnetosphere, and the interaction between the two is what ultimately produces the aurora. The solar wind is the fuel, the magnetosphere is the engine, and the aurora is the exhaust, the beautiful, luminous exhaust of a planet processing the breath of its star. Coronal mass ejections are the sun's most powerful explosions. The solar wind is constant, but it is not the whole story. Occasionally, the sun produces something far more dramatic, a coronal mass ejection, or CME. A CME is an enormous eruption of magnetized plasma from the sun's corona. Billions of tons of charged particles are hurled into space at speeds that can exceed 3,000 kilometers per second. The ejected material forms a vast cloud, often wider than the sun itself, expanding outward through the solar system like a cosmic shock wave. CMEs are triggered by instabilities in the sun's magnetic field. When magnetic field lines become twisted and stressed beyond their breaking point, they can snap and reconfigure in a process called magnetic reconnection. The energy stored in the twisted field is released explosively, launching plasma outward. The process is somewhat analogous to a rubber band that has been wound too tightly and suddenly snaps, releasing all its stored energy at once. Not all CMEs are directed toward Earth. The sun ejects them in all directions, and only those aimed roughly at our planet will have any effect. When a CME is Earth-directed, space weather forecasters can often predict its arrival 2 to 4 days in advance, giving satellite operators, power grid managers, and aurora watchers time to prepare. When an Earth-directed CME arrives, it compresses and distorts the magnetosphere, triggering a geomagnetic storm. These storms can last hours or even days, and they produce the most spectacular auroral displays, the kind that push the auroral oval to lower latitudes and fill the sky with colors visible even from places that normally never see the northern lights. The most powerful auroral events in recorded history, the ones that turn the sky red over Cuba or cause telegraph wires to spark in New York, were all driven by massive CMEs. Oh, the aurora you see on a quiet night is the sun whispering. A CME-driven aurora is the sun shouting. Sunspots are windows into the sun's magnetic chaos. If you could safely look at the sun's surface through a telescope with a proper solar filter, you would occasionally see dark spots, regions that appear darker than their surroundings. These are sunspots, and they have been observed and recorded for over 2,000 years, with Chinese astronomers noting them as early as 28 BCE. Sunspots are not truly dark. They are still blazingly bright, with temperatures around 3,500 degrees Celsius, but they appear dark because the surrounding photosphere is about 5,500 degrees. The contrast makes them look like dark blemishes on the solar surface. The cause of sunspots is magnetic, and they form where intense magnetic field lines emerge through the photosphere, inhibiting the normal convective flow of plasma that carries heat from the interior to the surface. The magnetic field acts like a plug, suppressing the rising hot plasma and creating a region that is slightly cooler and therefore slightly dimmer than its surroundings. Sunspots typically appear in pairs or groups, with each pair connected by a magnetic loop arching through the corona. These magnetic loops are the structures that can become unstable and produce solar flares and coronal mass ejections. The more sunspots there are, the more complex the sun's magnetic field, and the more likely it is to produce the eruptions that drive geomagnetic storms and auroras. The number of sunspots rises and falls in a cycle of approximately 11 years, a rhythm that has been tracked continuously since the early 18th century. At solar minimum, the sun may go weeks or months without a single visible sunspot. At solar maximum, dozens may be present simultaneously, and the sun's magnetic activity reaches its peak. The aurora follows this cycle faithfully. During solar maximum years, auroras are more frequent, more intense, and visible at lower latitudes. During solar minimum, they retreat toward the poles and become quieter. The sun has an 11-year cycle of activity. The solar cycle is one of the most regular rhythms in astrophysics. Approximately every 11 years, the sun's magnetic activity rises from a quiet minimum to a turbulent maximum, and then subsides again. And this cycle affects everything from the number of sunspots to the frequency of solar flares to the intensity of the aurora. The cycle is driven by the sun's internal magnetic dynamo, a process in which the differential rotation of the sun, rotating faster at the equator than at the poles, stretches, tangles, and amplifies the magnetic field over time. At the beginning of a cycle, the field is relatively simple, roughly aligned with the sun's rotation axis. As the cycle progresses, the field becomes increasingly complex, twisted and knotted by the sun's rotation, until it reaches a state of maximum complexity at solar maximum. At solar maximum, the sun's magnetic field eventually becomes so tangled that it undergoes a dramatic reorganization. The magnetic poles flip. The north magnetic pole becomes the south, and when the south becomes the north. This reversal happens every 11 years, meaning that the full magnetic cycle, from one polarity to the same polarity again, is actually 22 years. The solar cycle was first identified by the German astronomer Heinrich Schwabe in 1843. After 17 years of meticulous daily sunspot observations. Schwabe was not looking for a solar cycle. He was looking for a planet orbiting inside Mercury's orbit. He never found the planet, but his careful records revealed the rhythmic rise and fall of sunspot numbers that we now call the Schwabe cycle. For aurora watchers, the solar cycle is the fundamental calendar. The years around solar maximum, typically a 2 to 3 year window, offer the best chances of seeing strong auroral displays. The current solar cycle, Cycle 25, began in December 2019 and is expected to reach its maximum around 2025, making the coming years an excellent time to look north. Solar flares release energy equivalent to billions of nuclear weapons. A solar flare is a sudden, intense burst of electromagnetic radiation from the sun's surface, typically originating near sunspot groups where the magnetic field is most complex and stressed. When magnetic field lines in the corona become twisted to the point of instability, they can undergo rapid reconnection, releasing enormous amounts of stored magnetic energy in a matter of minutes. This energy is converted into radiation across the entire electromagnetic spectrum, from radio waves to visible light to ultraviolet to X-rays and even gamma rays. The most powerful flares release energy equivalent to billions of hydrogen bombs detonating simultaneously. Solar flares are classified by their X-ray brightness. C-class flares are small and have few noticeable effects on Earth. M-class flares are moderate and can cause brief radio blackouts at high latitudes. X-class flares are the most powerful, capable of causing widespread radio disruptions, degrading GPS accuracy, and posing radiation risks to astronauts. Unlike coronal mass ejections, which send physical material across space at relatively slow speeds, the electromagnetic radiation from a solar flare travels at the speed of light. It reaches Earth in just 8 minutes with no advance warning. The first sign of a flare's arrival is often a sudden increase in X-ray flux detected by satellites, followed within minutes by disruptions to high-frequency radio communications on the sunlit side of the Earth. Solar flares and CMEs often occur together, but they are distinct phenomena. A flare is a flash of radiation. A CME is a cloud of plasma. The flare arrives first at light speed. The CME arrives days later at the speed of the solar wind. It is the CME that produces the geomagnetic storm and the aurora. The flare is the announcement. The CME is the main event. The solar wind takes days to reach Earth, and that delay is a gift. When a coronal mass ejection erupts from the sun and begins its journey toward Earth, a clock starts. The plasma cloud, vast and magnetized, races outward through the solar system at speeds that can range from a few hundred to over 3,000 kilometers per second. At typical speeds, it will reach Earth in 2 to 4 days. This transit time is enormously important because it gives us a window of warning. Space weather forecasting agencies, including NOAA's Space Weather Prediction Center in the United States and the European Space Agency's Space Weather Service, monitor the sun continuously using a fleet of space-based observatories. When an Earth-directed CME is detected, forecasters can estimate its speed, density, and magnetic orientation, and issue warnings to satellite operators, airlines, power grid managers, and yes, aurora enthusiasts. The key satellite for this early warning system is the Deep Space Climate Observatory, or DSCOVR, which orbits the Sun at the first Lagrange point, L1, about 1.5 million kilometers sunward of Earth. DSCOVR measures the solar wind in real time, which providing roughly 15 to 60 minutes of advance notice before a CME or solar wind disturbance reaches Earth. 15 minutes is not much time for a power grid operator to prepare, but it is enough to take protective measures, to disconnect vulnerable transformers, to adjust satellite orbits, to warn astronauts to seek shelter. The aurora itself needs no warning. It simply arrives, the magnetic field responds, and the sky lights up. But for the technological infrastructure of modern civilization, those few minutes of notice can mean the difference between an inconvenience and a catastrophe. The Parker Solar Probe is flying through the sun's atmosphere. In August 2018, NASA launched the Parker Solar Probe, a spacecraft designed to do something that had never been attempted before. To fly through the sun's outer atmosphere and study the solar wind at its source. The probe is named after Eugene Parker, the physicist who first predicted the existence of the solar wind in 1958. Parker, then 91 years old, was present at the launch, making it the first NASA mission named after a living person. He watched his theoretical prediction take physical form as a spacecraft designed to plunge into the very phenomenon he had described 6 decades earlier. The Parker Solar Probe uses a series of gravitational assists from Venus to gradually shrink its orbit, bringing it closer and closer to the sun with each pass. At its closest approach, the probe passes within about 6 million kilometers of the solar surface, well inside the corona. At that distance, the sun appears 13 times larger in the sky than it does from Earth, and the sunlight is 500 times more intense. To survive this environment, the probe is equipped with a heat shield made of carbon composite, roughly 11 centimeters thick, which faces the sun at all times. The front of the shield reaches temperatures of about 1,400 degrees Celsius, while the instruments behind it remain at a comfortable 30 degrees. The engineering is extraordinary, a spacecraft that can fly through a star's atmosphere and survive. The Parker Solar Probe has already made groundbreaking discoveries. It has found that the solar wind near the sun is far more turbulent and structured than expected, with sudden reversals in the magnetic field direction called switchbacks. It has measured the boundary where the solar wind transitions from sub-alphenic to superalfvenic flow, effectively crossing the threshold of the sun's corona. It is, in a very real sense, touching the sun, and everything it learns about the solar wind, its structure, its speed, its magnetic complexity, feeds directly into our understanding of the aurora. The more we understand the sun's breath, the better we understand the lights it paints on our sky. Earth has an invisible shield, and without it, we would have no atmosphere. Between the sun and the aurora stands a barrier. You cannot see it, hear it, or feel it, but it is there, surrounding the entire planet, extending tens of thousands of kilometers into space. It is the magnetosphere, the region of space dominated by Earth's magnetic field. The magnetosphere is what makes the aurora possible. Without it, the solar wind would strike the atmosphere directly, gradually stripping it away over millions of years. This is not speculation, it is history. Mars once had a thicker atmosphere and possibly liquid water on its surface. But Mars lost its global magnetic field billions of years ago, and without that protection, the solar wind slowly eroded its atmosphere, leaving the thin, cold remnant we see today. Earth's magnetic field resembles the field of a simple bar magnet, with field lines emerging from the south magnetic pole, arching through space and re-entering at the north magnetic pole. Near the surface, this dipole approximation is reasonably accurate, but farther from Earth, the field is dramatically distorted by the solar wind. On the side facing the sun, the magnetosphere is compressed by the pressure of the solar wind to a distance of about 10 Earth radii, roughly 64,000 kilometers. On the opposite side, the night side, the magnetic field is stretched into a long tail, the magnetotail, extending hundreds of Earth radii downstream. The magnetosphere is not a sphere at all. It is shaped like a comet, blunt on one side and elongated on the other, sculpted by the relentless pressure of the sun's exhaled particles. This magnetic cocoon is your shield. It deflects the vast majority of the solar wind around the planet, the way a rock in a stream deflects water. Most of the charged particles in the solar wind never reach the atmosphere. They flow around the magnetosphere and continue on their way into the outer solar system, never knowing that a world full of life was hiding behind an invisible wall of magnetic force. The magnetic field is generated by liquid iron 5,000 kilometers beneath your feet. The source of Earth's magnetic shield is not at the surface. It is not in the crust. It is deep beneath you, at the very center of the planet, where the conditions are so extreme that iron behaves like a liquid ocean. Earth's interior is layered. The outermost layer, the crust, is a thin shell of solid rock, ranging from about 5 to 70 kilometers thick. Below the crust is the mantle, a thick layer of hot, slowly flowing silicate rock that extends down to about 2,900 kilometers. And below the mantle is the core, divided into two parts. The inner core, a solid sphere of iron and nickel about 1,200 kilometers in radius, sits at the very center, under pressure so immense that the iron remains solid despite temperatures exceeding 5,000 degrees Celsius. Surrounding the inner core is the outer core, a layer of liquid iron and nickel about 2,200 kilometers thick. It is the outer core that generates the magnetic field. The liquid iron is electrically conductive, and it is in constant motion, driven by convection, heat escaping from the inner core, and the Coriolis force from Earth's rotation. These motions create electric currents, and electric currents create magnetic fields. The process is self-sustaining. The magnetic field itself influences the flow of the liquid iron, which in turn sustains the magnetic field. This is the geodynamo, one of the most complex and beautiful examples of self-organizing physics in the natural world. And the geodynamo has been operating for at least 3.5 billion years, based on evidence from ancient rocks that preserve the orientation of the magnetic field at the time they cooled. For most of Earth's history, this invisible engine has been running beneath the surface, generating the field that shields the atmosphere, guides the aurora, and allows compasses to point north. You cannot see the outer core. You cannot hear it. You will never visit it. But every aurora that has ever danced across the sky was ultimately powered by the slow, churning motion of liquid iron 5,000 kilometers below your feet. The magnetosphere is shaped like a windsock, compressed on one side and stretched on the other. If the Earth existed in empty space, with no solar wind, its magnetic field would extend symmetrically in all directions, forming a perfect dipole pattern, like the field of a bar magnet in a physics classroom. But the Earth does not exist in empty space. It exists in the solar wind, and the solar wind reshapes the magnetosphere into something far more interesting. On the day side, facing the sun, the solar wind rams into the magnetic field with tremendous pressure. This compresses the magnetosphere, pushing the outer boundary, called the magnetopause, inward to a distance of about 10 Earth radii. The magnetopause is not a physical wall. It is the surface where the pressure of the Earth's magnetic field exactly balances the pressure of the incoming solar wind. Inside the magnetopause, Earth's field dominates. Outside it, the solar wind rules. On the night side, away from the sun, the magnetic field is not compressed but stretched, and the solar wind flowing past the Earth drags the magnetic field lines backward, pulling them into a long, thin structure called the magnetotail. The magnetotail extends hundreds of Earth radii into space, reaching far past the orbit of the Moon on the night side. It is within this magnetotail that much of the energy storage and release that drives the aurora takes place. The magnetotail is divided by a thin sheet of plasma called the plasma sheet, where magnetic field lines from the northern and southern hemispheres are nearly anti-parallel, pointing in opposite directions with only a thin layer of current separating them. This configuration is inherently unstable, like two magnets held close together with opposing poles nearly touching. When the stored energy becomes too great, the field lines snap and reconnect, releasing energy explosively and sending charged particles racing down toward the poles, where they create the aurora. The magnetosphere is not a static structure. It is a dynamic, breathing system, constantly adjusting to the changing pressure and magnetic orientation of the solar wind. Every gust of solar wind reshapes it. Every CME impact compresses it, and every reconnection event in the magnetotail sends energy flooding toward the atmosphere, painting the sky with light. When the solar wind strikes the magnetosphere, something dramatic happens. A coronal mass ejection has crossed 150 million kilometers of space and reached Earth. The magnetized plasma cloud slams into the magnetopause, compressing it inward, sometimes to half its normal distance. The entire magnetosphere shudders. Magnetic field lines that had been stable for hours or days are suddenly stressed, stretched, and twisted by the incoming pressure. This is a geomagnetic storm, and it is the engine that drives the most spectacular auroras. The key to the aurora lies not in the compression itself, but in what happens next, in the magnetotail on the night side of Earth. The solar wind drags magnetic field lines backward, stretching the magnetotail like a rubber band pulled further and further from its resting position. Energy accumulates in the tail, stored in the increasingly stressed magnetic configuration. The system is loading, building pressure, approaching a threshold, and then it breaks. Magnetic reconnection is the spark that lights the aurora. When the stretched magnetic field lines in the magnetotail can no longer sustain the accumulated stress, they snap. Field lines from the northern and southern hemispheres, which had been pointing in nearly opposite directions across the thin plasma sheet, suddenly break apart and reconnect in a new configuration. This process, magnetic reconnection, releases enormous energy in seconds. The stored magnetic energy is converted into kinetic energy, heat, in the acceleration of charged particles. Electrons and protons that had been trapped in the magnetotail are suddenly flung at tremendous speeds along the newly reconnected field lines, racing toward Earth's magnetic poles. Reconnection is not a gentle process. It is explosive, sudden, and it transforms the magnetotail from a quietly loaded energy reservoir into a particle accelerator aimed directly at the atmosphere. The particles that will become the aurora are born in this moment, accelerated from near rest to energies of thousands of electron volts in a matter of seconds. This is why auroras often appear suddenly. The sky can be dark and quiet for hours, and then, within minutes, curtains of light erupt across the horizon. The reconnection event in the magnetotail is the trigger, and the aurora is its visible consequence. Charged particles spiral down magnetic field lines toward the poles. The electrons, accelerated by magnetic reconnection, do not travel in straight lines. They follow the magnetic field, and their motion is a tight spiral, corkscrewing around the field line as they race toward Earth. This helical motion is called gyration, and its radius depends on the particle's energy and the strength of the magnetic field. As the electrons approach the poles, the magnetic field lines converge, funneling the particles into an increasingly narrow region. The field strength increases, and some particles are reflected back, bouncing between the northern and southern hemispheres in a motion called magnetic mirroring. But the most energetic particles punch through the mirror points and plunge into the atmosphere. They arrive at altitudes between 100 and 300 kilometers, where the atmosphere is thin enough to allow the particles to penetrate, but dense enough to provide gas atoms for them to collide with. This is the auroral zone, the narrow altitude band where the sky produces light. The geometry of the magnetic field determines where on Earth the aurora appears. Because the field lines converge at the magnetic poles, the aurora forms an oval-shaped ring around each pole, typically between 65 and 75 degrees magnetic latitude. During strong geomagnetic storms, the oval expands, pushing equatorward, and the aurora becomes visible at lower latitudes. The aurora happens simultaneously at both poles. The northern lights have a twin. While the Aurora Borealis dances across Arctic skies, the Aurora Australis performs an almost identical display above the Antarctic. The two auroras are connected, mirror images driven by the same solar wind, the same magnetic reconnection, the same particles spiraling down the same field lines toward opposite ends of the Earth. Satellite observations have confirmed that the two auroral ovals are remarkably symmetric during quiet conditions. A bright arc over northern Scandinavia corresponds to a matching arc over the Southern Ocean. A substorm breakup over Canada is mirrored by a breakup over Antarctica. During disturbed conditions, however, the symmetry can break down. Differences in the magnetic field geometry between the two hemispheres and asymmetries in the incoming solar wind can cause the northern and southern auroras to differ in brightness, position, and timing. And the two displays are siblings, not identical twins. Very few people have ever seen both auroras. The Aurora Australis is far less observed than its northern counterpart, simply because there is very little inhabited land at the high southern latitudes where it occurs. Antarctica, the Southern Ocean, and the southern tips of New Zealand, Australia, and South America offer occasional glimpses, but the northern lights remain far more accessible to human eyes. Each photon of aurora light is born from a single atom. Let us now descend from the vastness of the magnetosphere to the intimate scale of individual atoms. Because the aurora, for all its grandeur, is ultimately built from the smallest possible events. A single electron, accelerated in the magnetotail and guided by the magnetic field, arrives in the upper atmosphere. It collides with a single oxygen atom. The collision does not destroy the atom or the electron. Instead, it transfers energy, bumping one of the atom's own electrons to a higher energy level. The oxygen atom is now excited, carrying more energy than it wants. The atom holds this energy for a brief moment. Then it relaxes, its electron falling back to a lower energy level, and the excess energy is released as a single photon. One particle of light, one tiny flash, invisible to the naked eye, carrying a specific wavelength determined by the quantum mechanics of the oxygen atom. This is the fundamental unit of the aurora. Everything you see in the sky, every curtain, every arc, every corona, is the sum of trillions of these individual atomic events happening simultaneously across a vast region of the upper atmosphere. And the aurora is not a continuous glow. It is a chorus of individual voices, each one an atom releasing a single photon, together creating something that fills the sky. Oxygen atoms are patient, and their patience determines the color. When an oxygen atom is excited by a collision, it does not release its photon immediately. The specific electronic transitions that produce auroral light are what physicists call forbidden transitions, meaning they are quantum mechanically unlikely. The atom must wait. For the green emission at 557.7 nanometers, the oxygen atom waits about 0.7 of a second. This may not sound like much, but in the dense lower atmosphere, where collisions between molecules occur billions of times per second, 0.7 of a second is an eternity. At low altitudes, the excited oxygen atom would be struck by another molecule long before it could emit its green photon, and the energy would be lost as heat rather than light. This is why the green aurora appears at altitudes above 100 kilometers. Only there is the atmosphere thin enough for the oxygen atom to wait undisturbed for the fraction of a second it needs. For the red emission at 630 nanometers, the wait is far longer, up to 2 minutes. This transition is even more forbidden, even more unlikely, and requires even thinner atmosphere. Red auroral emission occurs only above 300 kilometers, where the gas is so sparse that an oxygen atom can hold its excited state for minutes without being disturbed. The patience of oxygen atoms paints the sky. Green where the wait is short and the atmosphere moderately thin. Red where the wait is long and the atmosphere nearly empty. The colors are not arbitrary. They are a direct readout of altitude, atmospheric density, and the quantum mechanical properties of a single element. Nitrogen adds the lower colors. While oxygen dominates the auroral palette, nitrogen contributes essential colors to the display. Nitrogen molecules and atoms produce the blue, violet, and pink tones that appear primarily at lower altitudes. When a nitrogen molecule is ionized by a high-energy particle, losing one of its electrons entirely, it emits light in the blue and violet range. This emission occurs around 100 kilometers altitude, where the atmosphere is dense enough to contain abundant nitrogen. The result is the purple and magenta fringe often visible along the lower edge of auroral curtains. Neutral nitrogen atoms, when excited, emit in the red-pink part of the spectrum, producing colors distinct from the oxygen red. This nitrogen pink appears at the very lowest edges of the aurora, where the most energetic particles have penetrated deepest into the atmosphere. The full auroral display is a vertical painting. Red oxygen at the top, green oxygen in the middle, blue-violet nitrogen at the bottom, pink nitrogen at the very base. Each layer a different gas, a different altitude, a different quantum transition. Together they create the multicolored spectacle that makes strong auroras so unforgettable. Billions of tiny flashes create the glow you see. No human eye could ever detect a single auroral photon. The flash from one oxygen atom returning to its ground state is unimaginably faint. But the aurora is not one atom. It is billions upon billions, all excited at once, all releasing photons in the same narrow range of wavelengths, all contributing their individual whispers to a collective glow. The brightness of the aurora depends on the flux of incoming particles. More electrons arriving per second means more collisions, more excited atoms, more photons, and a brighter display. During quiet times, the particle flux is low and the aurora is faint. During geomagnetic storms, the flux increases dramatically and the aurora can become bright enough to read a newspaper by, casting visible shadows on the snow. The motion of the aurora, the rippling and folding and pulsing, reflects changes in the particle flux arriving from the magnetosphere. As reconnection events in the magnetotail send bursts of electrons toward the atmosphere, the aurora responds in real time, brightening, shifting, and dancing in patterns that trace the invisible dynamics of the magnetic field above. The altitude determines the color, and you can read it like a map. If you know the physics, the aurora becomes a readable instrument. Each color corresponds to a specific altitude and a specific atmospheric gas. Look at an aurora and you are seeing a cross-section of the upper atmosphere, illuminated from within. Below 100 kilometers, blue and purple nitrogen emissions dominate. Between 100 and 300 kilometers, the bright green of oxygen fills the sky. Above 300 kilometers, the rare red of high-altitude oxygen appears. The boundaries are not sharp but gradual, one color fading into another as altitude changes. Proton auroras add another invisible layer. Protons entering the atmosphere undergo charge exchange with neutral atoms, becoming neutral hydrogen and then reionizing, producing a diffuse glow in hydrogen emission lines. This glow is spread over a wide area and is too faint for the naked eye, detectable only by specialized instruments. Every auroral display is a scientific instrument hanging in the sky, broadcasting information about the energy of the incoming particles, the density and composition of the atmosphere, and the structure of the magnetic field. Scientists have been reading this instrument for over a century, and it continues to reveal new details about the complex interaction between the sun and the earth. The aurora is the atmosphere glowing, and you are looking at excited air. Step back for a moment and consider what you are actually seeing when you look at the aurora. You are not seeing reflected sunlight. You are not seeing light from space. You are seeing the atmosphere itself producing light, atoms of oxygen and nitrogen emitting photons as they return to their ground states after being excited by collisions with charged particles. The physics is identical to what happens inside a neon sign. In a neon tube, an electric current passes through a low-pressure gas, exciting the atoms, which then emit characteristic colors as they de-excite. Neon produces red-orange. Argon produces blue. Mercury vapor produces ultraviolet, which is then converted to visible light by phosphor coatings. The aurora is a neon sign the size of a continent. The gas is the atmosphere. The electric current is the stream of charged particles from the magnetosphere, and the resulting light is not artificial but natural, produced by the same quantum mechanical processes that govern every light-emitting atom in the universe. You are looking at excited air. That is all the aurora is. And the fact that excited air can be this beautiful, this vast, this capable of moving people to tears, is perhaps the most remarkable thing about it. Ancient people saw gods dancing in the sky. For most of human history, the aurora had no scientific explanation. It was a mystery, a wonder, a source of awe and often of fear. Every culture that encountered it created stories to explain the lights, stories that reveal as much about the human imagination as they do about the phenomenon itself. The aurora appears predominantly at high latitudes, which means the cultures with the richest auroral traditions are those of the Arctic and subarctic regions. The Norse, the Sámi, the Inuit, the Cree, the Finnish, the Scottish, and the Icelandic peoples all developed elaborate mythologies around the lights. At lower latitudes, where auroras appeared only during the most powerful geomagnetic storms, the lights were rarer and therefore more alarming, often interpreted as portents of war, famine, or divine displeasure. What unites nearly all auroral mythology is a sense that the lights are alive. They move, they change. They respond to the night in ways that feel purposeful, even intelligent. It is difficult to watch the aurora and not feel that something is watching you back. This sense of presence, of being in the company of something vast and aware, it runs through auroral folklore across every continent where the lights have been observed. The Norse saw a bridge to the realm of the gods. In Norse mythology, the aurora was associated with the Bifrost, the burning rainbow bridge that connected Midgard, the world of humans, with Asgard, the realm of the gods. The Bifrost was guarded by Heimdall, the ever-watchful sentinel with hearing so keen he could detect grass growing and sight so sharp he could see to the ends of the earth. The connection between the aurora and the Bifrost is not explicitly stated in the primary Norse sources, the prose Edda and the poetic Edda. But the association has become deeply embedded in Scandinavian cultural tradition. The shimmering bridge-like arcs of the aurora, spanning the sky from horizon to horizon, would naturally evoke the image of a celestial crossing. Other Norse traditions associated the aurora with the Valkyries, the warrior maidens who chose the slain on the battlefield and carried them to Valhalla. The flickering lights were the reflections from the Valkyries' armor as they rode across the sky, selecting the bravest of the fallen. In this interpretation, the aurora was not merely beautiful. It was sacred, a visible sign that the gods were at work, that heroes were being honored, that the boundary between the living and the dead was thinner than usual. The Sámi treated the lights with deep respect and caution. The Sámi people, the indigenous inhabitants of northern Scandinavia in the Kola Peninsula, have lived beneath the aurora for thousands of years. Their relationship with the lights is one of the most intimate and most reverent of any culture on Earth. In many Sámi traditions, the aurora was believed to be the spirits of the dead. The lights were not entertainment. They were ancestors and they demanded respect. You did not whistle at the aurora. You did not wave at it. You did not draw attention to yourself. To do so was to risk angering the spirits who might reach down and carry you away. Children were brought inside when the lights were strong. Bright clothing was avoided. Some communities believed that the aurora could hear you, that it would respond to sounds swooping lower if you whistled or clapped. This was not considered a good thing. The spirits were powerful and unpredictable, and the wise response was quiet observation, humility, and a certain healthy fear. These beliefs are not merely historical. Some Sámi communities maintain a respectful relationship with the aurora to this day. The lights are not just a natural phenomenon to be photographed and posted on social media. They are part of a living cultural landscape, a connection to ancestors, a reminder that the sky is not empty, but populated. In East Asia, red auroras were omens of catastrophe. At lower latitudes, the aurora is rare. When it does appear, it is almost always red, because only the most powerful geomagnetic storms push the auroral oval far enough south to be visible, and the high-altitude red emission of oxygen is the color most likely to be seen from a distance. In China, red auroras were recorded as early as the 2nd millennium BCE. They were interpreted as celestial fires, dragons in the sky, or signs of heavenly displeasure. A red glow in the northern sky, appearing without explanation over a civilization that had never seen one before, was naturally terrifying. In Japan, a red aurora was sometimes interpreted as a celestial foxfire, associated with the mythical kitsune. In other traditions, it was a sign that a great battle was being fought in the heavens, or that the emperor had lost the mandate of heaven. In medieval Europe, red auroras were similarly feared. Chronicles from the Middle Ages describe nights when the northern sky turned blood red, causing panic, prayer, and processions through the streets. The Nuremberg Chronicle of 1493 includes illustrations of celestial phenomena that appear to depict auroral displays, interpreted as warnings from God. The fear was not irrational. A red sky at night, it appearing suddenly and without warning, violating everything people knew about how the sky should behave, was genuinely alarming. Without any understanding of solar physics or geomagnetism, a red aurora looked exactly like the sky was on fire. Galileo named them, but got the science wrong. The term Aurora Borealis was first used by the Italian astronomer Galileo Galilei in 1619. He combined Aurora, the Roman goddess of the dawn, with Boreas, the Greek god of the north wind, creating a name that translates roughly as Northern Dawn. The name is beautiful and has endured for over 4 centuries, but Galileo's explanation of the phenomenon was incorrect. He believed that the aurora was caused by sunlight reflecting off the atmosphere, a kind of twilight glow visible at high latitudes where the geometry of the sun's position below the horizon could illuminate the upper atmosphere. This was a reasonable hypothesis given the knowledge available in the early 17th century. The connection between the aurora and solar activity would not be established for another 2 centuries. The role of the magnetic field would not be understood until later still. Galileo saw the light correctly but misidentified its source. It is a common pattern in the history of science. The name outlives the explanation. We still call them the Northern Lights, still use Galileo's elegant Latin term, even though we now know that the lights have nothing to do with dawn and everything to do with charged particles from the sun colliding with atoms of oxygen and nitrogen in the upper atmosphere. When the name is a fossil, a beautiful artifact of a time when the aurora was still pure mystery. Halley connected the aurora to Earth's magnetic field. In 1716, the English astronomer Edmund Halley witnessed a strong auroral display over London. Halley was already famous for predicting the return of the comet that bears his name, and he brought the same analytical mind to the aurora. Halley noticed that the aurora appeared to align with the direction of the magnetic North Pole, and he proposed that the phenomenon was somehow related to Earth's magnetic field. He suggested that luminous magnetic effluvia escaping from the Earth's interior along magnetic field lines were responsible for the lights. His mechanism was wrong, but his observation was correct and enormously important. The aurora is indeed controlled by the magnetic field. It appears in an oval centered on the magnetic poles. Its curtains and rays align with magnetic field lines. Its position shifts as the magnetic field is disturbed by solar activity. Halley's contribution was to move the aurora from the realm of pure wonder into the realm of physical investigation. By connecting it to magnetism, he opened the door for future scientists to probe the actual mechanism. The path from Halley's observation to our modern understanding would take another 2 centuries, passing through the work of Celsius, Birkeland, Chapman, and many others. Christian Birkeland proved the sun was the source and was ignored. The most important figure in the history of aurora science is arguably the Norwegian physicist Christian Birkeland. Working at the turn of the 20th century, Birkeland conducted a series of brilliant experiments and expeditions that correctly identified the fundamental mechanism of the aurora decades before the scientific establishment was ready to accept it. Birkeland organized expeditions to northern Norway, establishing observation stations on remote mountaintops to study the aurora during the winter of 1899 to 1900. He endured brutal conditions, temperatures below -40, hurricane-force winds and isolation, to gather systematic measurements of auroral forms and their relationship to magnetic disturbances. Back in his laboratory, he constructed a device called the Terrella, a magnetized sphere placed inside a vacuum chamber. When he bombarded the sphere with electrons, luminous rings appeared around its magnetic poles, mimicking the auroral ovals. And the experiment was a stunning demonstration that charged particles from an external source, guided by a magnetic field, could produce auroral-like emissions. Birkeland proposed that the sun emitted streams of charged particles that were captured by Earth's magnetic field and directed toward the poles, where they excited atmospheric gases to produce light. This is, in essence, the correct explanation, but the scientific establishment rejected his ideas. The leading British geophysicist Sidney Chapman argued that space was a vacuum and that charged particles could not travel from the sun to the Earth. Chapman's authority dominated the field for decades, and Birkeland's work was largely forgotten. Birkeland died in 1917 in a hotel room in Tokyo, likely from an overdose of sleeping medication. He was exhausted, financially strained, and professionally isolated. It was not until the space age, when satellites directly measured the streams of charged particles flowing from the sun and the electric currents flowing along magnetic field lines into the aurora, that Birkeland was vindicated. Today, he is honored on the Norwegian 200 kroner banknote, his face beside his Torella experiment, and the northern lights he spent his life trying to understand. The Carrington event turned the sky red over the tropics. On September 1st, 1859, the English astronomer Richard Carrington was sketching sunspots through his telescope when he witnessed something unprecedented. A brilliant white flash erupted from the surface of the sun, lasting about 5 minutes. Carrington had observed a solar flare, the first ever recorded by a human being. 17 hours later, in the most powerful geomagnetic storm in recorded history struck Earth. The aurora was seen as far south as Cuba, Hawaii, Colombia, and central Mexico. In the northeastern United States, the sky was so bright with red and green light that people woke up thinking it was morning. Newspapers described the aurora as blood red, fire-like, and terrifying. The storm wreaked havoc on the only electrical technology of the era, the telegraph system. Telegraph operators reported sparks flying from their equipment. Some lines continued to operate even after being disconnected from their batteries, powered solely by the geomagnetically induced currents flowing through the wires. Some operators received electric shocks. At least one telegraph office caught fire. A Carrington-level event today would be catastrophic. A modern civilization depends on technologies that are vulnerable to geomagnetic storms. Power grids, satellite communications, GPS navigation, internet infrastructure, and aviation all could be severely disrupted. Estimates of the economic damage from a repeat Carrington event range from $1 to $2 trillion, with recovery times of months to years for the most affected systems. The Carrington event is a reminder that the aurora is not just a beautiful light show. It is the visible manifestation of an interaction between the sun and the earth that carries real power, power that can disrupt the technological infrastructure on which modern life depends. The 1989 storm blacked out an entire province. On March 13, 1989, a powerful coronal mass ejection struck Earth's magnetosphere and triggered a severe geomagnetic storm. Within 90 seconds, the entire power grid of the Canadian province of Quebec collapsed. 6 million people lost electricity. The blackout lasted 9 hours. The cause was geomagnetically induced currents, electrical currents generated in the ground and in long conductors like power lines by the rapidly changing magnetic field during the storm. These currents flowed into the power grid, overloading transformers and tripping circuit breakers in a cascading failure that brought the system down faster than operators could respond. The 1989 storm also damaged transformers as far south as New Jersey and caused disruptions to satellite communications worldwide. The aurora that night was visible from Texas and Florida, far south of its normal range. The Quebec blackout was a wake-up call for the power industry and for governments. It demonstrated that space weather is not merely an academic curiosity, but a genuine infrastructure risk. Since 1989, power grid operators have developed monitoring systems and operational procedures to reduce vulnerability to geomagnetic storms, but the fundamental risk remains. Long-distance power lines and high-voltage transformers are inherently susceptible to induced currents, and a sufficiently powerful storm could still cause widespread disruption. In May 2024, the aurora reached places that had never seen it before. In May 2024, during the rising phase of solar cycle 25, A series of powerful coronal mass ejections struck Earth in rapid succession, triggering the most intense geomagnetic storm in over 2 decades. The aurora was visible from locations that almost never see it: Mexico, Spain, Turkey, India, and parts of the southern United States. Social media exploded with photographs and videos. Millions of people who had never imagined seeing the aurora from their own backyards stepped outside and looked up to find the sky shimmering with color. The images spread globally within hours, and for a brief moment, the northern lights became the most shared natural phenomenon on the planet. The event demonstrated something important about the aurora. It is not confined to the Arctic. During sufficiently powerful storms, it can reach almost anywhere. The auroral oval expands equatorward as the magnetosphere is compressed, and the boundary of visible aurora can drop to latitudes of 30 or even 25 degrees. For people living at these latitudes, an aurora is a once-in-a-lifetime experience. They're a reminder that the sky is connected to forces far beyond the familiar cycle of day and night. Steve is not a traditional aurora, and citizen scientists discovered it. In 2016, members of a Canadian aurora photography group noticed something unusual in their images: a narrow, elongated streak of purple and white light stretching east to west across the sky, distinct from the usual auroral forms. They named it Steve. When scientists investigated, they discovered that Steve was not a conventional aurora at all. Unlike the aurora, which is caused by charged particles precipitating into the atmosphere from the magnetosphere, Steve appears to be caused by a fast-moving river of hot plasma in the ionosphere, a flow of ions at temperatures of 3,000 degrees Celsius, moving at speeds of 6 kilometers per second. When the phenomenon was officially named Steve, an acronym for Strong Thermal Emission Velocity Enhancement, and it has since been recognized as a distinct atmospheric optical phenomenon. Steve often appears equatorward of the main auroral oval and is frequently accompanied by a green picket fence structure, short vertical green streaks that appear beneath the main purple arc. Steve is a reminder that the sky still holds surprises, a phenomenon visible to the naked eye, photographed thousands of times by amateur aurora watchers. Went unrecognized by science until 2016. The discovery was driven not by professional astronomers with expensive equipment, but by curious citizens with cameras, patience, and a willingness to look carefully at what the sky was showing them. Auroras flicker at frequencies your eyes cannot detect. To the naked eye, the aurora appears to change slowly, drifting and folding over seconds and minutes. But high-speed cameras reveal a hidden world of rapid fluctuation. Auroras flicker at frequencies ranging from less than 1 hertz to over 100 hertz, far faster than the human eye can perceive. These rapid pulsations are driven by waves in the magnetosphere. Electromagnetic waves, plasma waves, and field line resonances all modulate the flow of charged particles into the atmosphere, causing the aurora to brighten and dim at frequencies determined by the physics of the magnetospheric plasma. One particular type of magnetospheric wave, called chorus waves, produces a distinctive pattern of pulsating aurora. Chorus waves are electromagnetic emissions generated by energetic electrons in the magnetosphere. When converted to audio frequencies, they sound remarkably like birdsong, a rising chirp repeated over and over. These waves scatter electrons into the atmosphere in periodic bursts, creating patches of aurora that blink on and off every few seconds. The aurora you see with your eyes is the slow, average version of a much more dynamic, rapidly flickering phenomenon. Beneath the graceful curtains and steady arcs, the light is pulsing with rhythms set by waves, propagating through the invisible plasma that fills the space around Earth. Substorms create the most dramatic aurora displays. The most spectacular aurora events are not gradual buildups, but sudden explosions of light. These are magnetospheric substorms, Episodes of rapid energy release in the magnetotail that sends surges of charged particles into the atmosphere within minutes. The substorm begins with a growth phase, during which energy from the solar wind is gradually stored in the magnetotail. The auroral arc at the poleward boundary of the oval may be quiet and stable during this phase, showing little activity, but the magnetotail is loading, building pressure, approaching instability. The onset is sudden. Magnetic reconnection in the tail releases the stored energy explosively. A surge of electrons races toward the atmosphere, and the quiet arc erupts. The aurora brightens dramatically, expands poleward and equatorward, and begins to display rapid motion, folding curtains, flickering patches, and bright rays shooting upward from the horizon. The expansion phase of a substorm can last 30 minutes to an hour, and it is during this phase that the aurora is at its most dynamic and most beautiful. The sky fills with movement, color, and energy. Curtains race across the horizon. Coronas bloom overhead. The entire display pulses with an urgency that contrasts sharply with the quiet buildup that preceded it. After the expansion, the aurora gradually calms in the recovery phase, returning to quieter forms and retreating poleward. The cycle can repeat multiple times during a single geomagnetic storm, each substorm releasing another burst of stored energy. Jupiter has the most powerful auroras in the solar system. Earth is not the only world with auroras. Throughout the solar system, wherever a planet has a magnetic field and an atmosphere, charged particles can excite gases and produce light. And nowhere is this process more dramatic than on Jupiter. Jupiter's magnetic field is approximately 20,000 times stronger than Earth's. Its magnetosphere is the largest structure in the solar system, so vast that if it were visible to the naked eye, it would appear larger than the full moon in Earth's sky. This colossal magnetic field captures charged particles not only from the solar wind, but from a source much closer to home, the volcanic moon Io. Io is the most volcanically active body in the solar system. Its volcanoes continuously eject sulfur dioxide into space, where it is ionized and swept up by Jupiter's rotating magnetic field. This volcanic material forms a donut-shaped ring of plasma around Jupiter called the Io plasma torus. The charged particles from this torus are accelerated along magnetic field lines toward Jupiter's poles, producing auroras that never switch off. Jupiter's auroras are hundreds of times more powerful than Earth's. They emit primarily in the ultraviolet and X-ray ranges, invisible to human eyes but spectacular in images from the Hubble Space Telescope and the Juno spacecraft. The auroral ovals are permanent features, glowing continuously, punctuated by bright spots that mark the magnetic footprints of Io and other large moons. Saturn's auroras dance to a different rhythm. Saturn also possesses a strong magnetic field and produces its own auroral displays, but they behave differently from both Earth's and Jupiter's. Saturn's auroras were first observed in ultraviolet light by the Hubble Space Telescope and later studied in detail by the Cassini spacecraft during its 13-year mission in the Saturn system. Saturn's auroras respond to the solar wind, but more slowly than Earth's. A surge in solar wind pressure can take days to produce a visible auroral response at Saturn, compared to hours at Earth. The auroral ovals are also more variable in shape and position, sometimes appearing as complete rings and sometimes as partial arcs. One of the most intriguing aspects of Saturn's auroras is that they emit strongly in infrared light, produced by excited hydrogen molecules in Saturn's upper atmosphere. Cassini detected these infrared emissions and used them to map the structure of Saturn's magnetosphere from the inside. Saturn also produces radio emissions associated with its auroral activity. These emissions, called Saturn kilometric radiation, pulse with a period that was initially thought to reflect Saturn's rotation rate, but later observations revealed that the period changes over time, suggesting that the radio emissions are driven not by the planet's rotation alone, but by complex interactions between the magnetosphere and the solar wind. Mars lost its aurora when it lost its magnetic field. Mars tells a cautionary tale about what happens when a planet loses its magnetic protection. Approximately 4 billion years ago, Mars had a global magnetic field generated by a dynamo in its core, similar to Earth's. But Mars is smaller than Earth, and its interior cooled more quickly. The dynamo shut down, the global field faded, and Mars was left exposed to the solar wind. Over the following billions of years, the solar wind gradually stripped away most of Mars's atmosphere. The thick, warm atmosphere that may once have supported liquid water on the surface was eroded into the thin, cold remnant that exists today, less than 1% the density of Earth's atmosphere. But Mars has not lost all traces of its magnetic past. Patches of magnetized rock in the Martian crust preserve the orientation of the ancient field, like fossils of a vanished magnetic shield. These crustal magnetic anomalies are strong enough to interact with the solar wind locally, and they produce small, patchy auroras above the regions where they occur. What NASA's MAVEN spacecraft has detected these discrete auroras on Mars, as well as diffuse auroras that occur across the planet's night side during solar storms. Mars's auroras are faint and localized, nothing like the vast curtains of Earth's display. They are the ghost lights of a planet that once had a shield and lost it. Uranus and Neptune have auroras that defy symmetry. The outer ice giants, Uranus and Neptune, present some of the strangest auroral geometries in the solar system. Both planets have magnetic fields, but unlike Earth, Jupiter, and Saturn, their magnetic axes are dramatically tilted relative to their rotation axes. Uranus's magnetic axis is tilted 59 degrees from its rotation axis, and its rotation axis itself is tilted 98 degrees from its orbital plane, meaning Uranus essentially rolls around the sun on its side. The result is a magnetic field that tumbles chaotically as the planet rotates, producing auroral ovals that wander across the surface in patterns unlike anything seen on other planets. Neptune's magnetic field is similarly tilted 47 degrees from the rotation axis and offset from the planet's center. Its auroras, observed briefly by Voyager 2 during its 1989 flyby, appeared at unusual latitudes and showed little resemblance to the neat ovals seen at Earth or Jupiter. These chaotic auroras remind us that Earth's relatively orderly display, with its symmetric ovals centered neatly on the magnetic poles, is not the norm. It is a consequence of Earth's particular magnetic geometry. On other worlds, the dance of charged particles and magnetic fields can produce auroral patterns that are wild, asymmetric, and constantly shifting. Exoplanets and brown dwarfs probably have auroras too. Beyond our solar system, auroras are almost certainly a universal phenomenon. Any world with a magnetic field and some form of atmosphere, whether gas, plasma, or ionized vapor, has the ingredients for auroral emission. Astronomers have already detected auroral-like radio emissions from several brown dwarfs, objects that straddle the boundary between large planets and small stars. These emissions are millions of times more powerful than Jupiter's and suggest that magnetic activity and particle acceleration are common in substellar objects. In 2015, radio observations of the brown dwarf LSRJ 1835+3259 revealed periodic radio pulses consistent with auroral emission from the object's magnetic poles. Optical observations confirmed a corresponding brightening in hydrogen alpha light, the signature of hydrogen atoms being excited by precipitating charged particles. It was the first confirmed detection of an aurora outside our solar system. As telescope technology improves, it may become possible to detect auroral emissions from exoplanets orbiting other stars. The aurora could become a tool for studying the magnetic fields of distant worlds, fields that are otherwise invisible across interstellar distances. Io's volcanic aurora is unique in the solar system. Jupiter's moon Io deserves special attention because it produces an aurora unlike anything else in the solar system. Our Io has a thin atmosphere composed primarily of sulfur dioxide, belched out by its continuously erupting volcanoes. As Io orbits within Jupiter's powerful magnetic field, this atmosphere is constantly being stripped, ionized, and swept into the surrounding plasma environment. The interaction between Io and Jupiter's magnetic field generates an electric current of about 3 million amperes flowing along the magnetic field lines connecting Io to Jupiter's poles. Where this current enters Jupiter's atmosphere, it produces a bright auroral spot, the Io footprint, a glowing patch that moves across Jupiter's polar region as Io orbits. The Io footprint has been observed by both Hubble and Juno, and its brightness and structure provide direct information about the electrical connection between Jupiter and its volcanic moon. It is a visible signature of a circuit that spans hundreds of thousands of kilometers, powered by the motion of a moon through a planet's magnetic field. Io also has its own faint aurora, produced by electron impacts on its sulfur dioxide atmosphere. This aurora is dim and localized, visible only in the data from passing spacecraft, but it confirms that even a tiny world with a thin volcanic atmosphere can produce light from the interaction of charged particles and gas. You are watching a star touch a planet. Let us pause here and consider what the aurora really is, stripped of all its technical detail and seen in its simplest form. A star, 93 million miles away, exhales. Its breath is made of charged particles, tiny fragments of its own substance, flung outward at 1 million miles per hour. And this breath crosses the void between worlds, a journey of days through empty space, and arrives at a small blue planet. The planet has a shield, a magnetic field generated by liquid iron churning in its core. The shield deflects most of the star's breath, but not all. Some particles slip through, guided by the field lines toward the poles. They descend through the thin upper atmosphere, striking atoms of oxygen and nitrogen. Each struck atom absorbs the energy, holds it for a moment, and releases it as light. That light is the aurora. It is a star touching a planet. It is the breath of the sun made visible by the atoms of the Earth. It is a connection across 150 million kilometers, written in photons, silent and beautiful and ancient. Every aurora you see, every green curtain, every violet edge, every red glow on the horizon is this same story, repeated endlessly, night after night, at both poles, on every planet with a magnetic field, perhaps on worlds orbiting distant stars that no human eye has ever seen. The magnetic field that protects you is ancient and impermanent. Earth's magnetic field has been operating for at least 3.5 billion years, shielding the atmosphere, guiding charged particles, and making the aurora possible. But it is not permanent. It fluctuates, it wanders, and periodically it reverses. Magnetic pole reversals are recorded in the geological record. When volcanic lava cools, the iron minerals within it align with the ambient magnetic field and preserve its direction. By studying ocean floor basalts, its geologists have reconstructed a detailed history of magnetic reversals stretching back hundreds of millions of years. The reversals are irregular. Some occur every few 100,000 years. Others are separated by tens of millions of years. The last reversal happened approximately 780,000 years ago, during the early Pleistocene. During a reversal, the field does not simply flip like a switch. It weakens, becomes complex and multipolar, and eventually reestablishes itself with the opposite polarity. The transition can take several thousand years. During this period, the weakened field provides less protection from the solar wind, and auroras would appear at unusual latitudes, possibly even near the equator. The field is currently weakening in some regions, particularly over the South Atlantic. Hoche, where a zone called the South Atlantic Anomaly has significantly reduced field strength. Whether this is a precursor to a reversal or simply normal fluctuation is not yet known. Most people on Earth will never see an aurora in person. The aurora is one of the most photographed and most desired natural experiences on the planet. Aurora tourism is a growing industry, drawing hundreds of thousands of visitors to northern Scandinavia, Iceland, Canada, and Alaska every winter. And yet, the vast majority of the human population will never see an aurora with their own eyes. The reasons are geographic and probabilistic. The auroral oval sits between 65 and 75 degrees magnetic latitude during quiet conditions. The world's population is concentrated between the tropics and the mid-latitudes, far from the auroral zone. Traveling to see the aurora requires time, money, tolerance for cold, and a willingness to endure cloudy skies and quiet solar conditions that may produce no display at all. Even for those who make the journey, success is not guaranteed. Cloud cover can obscure the sky for days. Solar activity can be low. The aurora may appear only briefly or only faintly, or only after midnight when exhaustion has driven you indoors. But the aurora does not need to be seen to be appreciated. Understanding it, knowing that it is there, knowing what produces it and why, knowing that this very night, above the Arctic Circle, green light is folding silently across the sky, this knowledge is its own kind of seeing. You do not need to stand in the cold to feel the wonder. You only need to know that the sky can dance, and that somewhere, right now, it is dancing. The lights are dancing right now as you listen. This is true. It is not poetry or metaphor. It is a statement of physical fact. At this moment, regardless of the time where you are, the auroral ovals are active at both poles of the Earth. The sun is continuously emitting solar wind. The magnetosphere is continuously processing it. Charged particles are continuously spiraling down magnetic field lines and colliding with atmospheric gases. Photons are being emitted, green and red and violet, in a display that never fully stops. The intensity varies. On quiet nights, the aurora may be nothing more than a faint arc near the magnetic pole, barely visible even to observers standing directly beneath it. On active nights, it may fill the sky with color from horizon to horizon, but it is always there in some form, and at some level, a permanent feature of Earth's interaction with the sun. Right now, over northern Norway, the sky may be glowing green. Over northern Canada, curtains may be swaying. Over Antarctica, the Aurora Australis may be painting the ice with violet light. You cannot see these things from where you are, but they are happening. The dance does not pause because no one is watching. The aurora does not perform, it simply happens. There is something profoundly comforting about a natural phenomenon that exists without purpose, without audience, without intent. The aurora does not try to be beautiful. It does not arrange itself for maximum visual impact. It does not care whether anyone is watching. Atoms are excited. Photons are released. Magnetic fields guide particles along invisible paths. The result is beautiful. But the beauty is incidental. It is a byproduct of physics, an accident of quantum mechanics and electromagnetism and orbital mechanics and planetary geology, all converging in a single atmospheric layer to produce light that happens to be visible to the particular arrangement of cells in the human retina. The universe is not trying to be beautiful, but beauty keeps emerging anyway, in the spiral of a galaxy, in the symmetry of a snowflake, in the green glow of excited oxygen 100 kilometers above the Arctic. The aurora is one of countless examples of the universe, producing something magnificent without meaning to, without trying, without even knowing. And perhaps that is the most beautiful thing of all. Not that the sky dances, but that the sky would dance exactly the same way if no one were there to see it. Close your eyes and let the lights dance behind your eyelids. Imagine now that you are lying on your back in fresh snow. The cold does not bother you. The air is perfectly still. Above you, the sky is the deepest black you have ever seen, filled with stars so bright they seem close enough to touch. And then, at the edge of your vision, a faint green glow appears. It grows slowly, reaching upward like a hand stretching toward the stars. The green deepens and begins to move, rippling gently, folding over itself like a curtain caught in the slowest breeze imaginable. A second curtain appears, this one edged with violet. It moves independently of the first, the two of them swaying in a rhythm that has no pattern, no repetition, no beginning, and no end. The violet deepens to purple at the edges. A faint red blush appears at the very top of the display, barely there, like the last trace of color in a sunset that has already ended. The lights make no sound. The only thing you can hear is your own breathing, slow and steady and warm against the cold air. The sky moves above you like water, like music made visible, like something dreaming. You do not need to understand it right now. You do not need to remember the physics, the wavelengths, the altitudes, the names of the gases. All of that will be there tomorrow. Tonight, the lights are just lights, green and violet and red, moving across the sky with the patience of something that has been doing this for 4.5 billion years and will continue for billions more. Let them move. Let them fold and ripple and fade and return. Let your breath match their rhythm, on a slow and deep and unhurried. The lights do not need you to watch them. They do not need you to understand them. They only need you to rest. And now let the northern lights carry you gently towards sleep. We have traveled far tonight. We began beneath a frozen sky, watching curtains of green light sway across the darkness. We traced the aurora backward, from the atmosphere to the magnetosphere, from the magnetic field to the liquid iron core, from the Earth across 150 million kilometers of space to the surface of the sun. We learned that the aurora is born in violence, in the magnetic chaos of a star, in explosions that fling billions of tons of plasma across the solar system. But by the time that violence reaches Earth, it has been transformed into something gentle. The magnetosphere absorbs the shock. The magnetic field guides the particles. The atmosphere receives them quietly, atom by atom, and responds with the softest possible thing, light. We heard the stories that ancient cultures told about the lights, bridges to the gods, spirits of the dead, omens of fire and war. We met the scientists who slowly unraveled the mystery, from Halley to Birkeland to the satellite era. And we discovered that the aurora is not unique to Earth, that it dances on Jupiter and Saturn, on the ice giants, on volcanic moons, and probably on worlds orbiting stars we have not yet named. Through it all, a single quiet truth kept returning. The aurora is a connection. It is the visible thread between a star and a planet, between the sun's magnetic breath and the Earth's atmospheric reply. It is physics made beautiful, energy made visible, violence made gentle. You carry this connection within you. The iron in your blood was forged in stars. The oxygen you breathe is the same oxygen that glows green 100 kilometers above your head. The magnetic field that shields you and makes the aurora possible is generated by the same element, iron flowing as liquid 5,000 kilometers beneath your feet. You are made of the same things that make the aurora. You are part of the same story. Tonight, as you rest, the lights continue. Over Tromsø and Fairbanks and Yellowknife, over the Southern Ocean and the Antarctic ice sheet, the sky is glowing. Green curtains are folding. Violet edges are flickering. Red light is blooming at altitudes where the air is thinner than the best vacuum you could create in a laboratory. You do not need to see them. You do not need to travel to find them. You only need to know that they are there, that they are always there, that every night the sun reaches out and the earth responds with light. Let that knowledge be soft tonight. Let it be a blanket, not a lesson. Let the colors fade slowly in your imagination, green dissolving into darkness, violet melting into quiet, red dimming to the faintest possible glow before it too slips away. Sleep well. The lights will dance again tomorrow night. They danced last night. They danced a billion years ago. They will dance a billion years from now. They do not tire. They do not stop. They do not need you to watch, but they are glad you listened. Good night.